Welcome back to the deep dive. Today we are taking a fascinating plunge into a topic that affects every single one of us, every minute of the day.
It really does.
Yet we rarely stop to truly analyze it. The weather and the seasons.
Right.
It's the ultimate universal conversation starter, but the vocabulary, the science, and, the cultural nuances behind it are surprisingly deep.
It truly is. I
Yeah.
mean, we often take the topic for granted, assuming we know what we mean when we talk about a scorcher or a heavy rain.
Mhm.
But your sources reveal a rich, targeted language that meteorologists and, well, great conversationalists use to convey precise meaning.
Absolutely. We have this excellent stack of material here covering everything from the technical definitions of cloud types and precipitation all the way to the grand cycles of climate and even how weather defines human culture through idioms.
And our mission, really, is to transform that knowledge into practical conversational power. Understanding the difference between a gale and a breeze, or why humidity makes heat feel unbearable, it doesn't just make you better at planning your outfit. It gives you immediate context for connection and confidence.
That's the key takeaway right there. Talking about the weather is the ultimate social lubricant.
It is.
It's non-controversial, it's constantly relevant, and it bridges social gaps. So by the end of this deep dive, you, our listener, will have the complete vocabulary and context needed for any weather-related small talk, for understanding any forecast, making you instantly well-informed.
It is, quite literally, the groundwork of human connection worldwide. Mastering this vocabulary is a fundamental skill that pays dividends every single day.
Okay, let's unpack this. Let's start with geographic extremes, because I think nothing defines the difference between today's condition and the long-term pattern better than contrasting two locations on a map.
A perfect place to start.
When we talk about weather, we are talking about today. But when we talk about climate, we're talking about the expected normal. The sources brilliantly use two dramatically different U.S. cities to highlight this.
They do.
Portland, Oregon versus San Diego, California.
It's the perfect geographical microcosm for this discussion. Let's start with Portland, Oregon, the rainy extreme up in the Pacific Northwest.
Right.
While people often associate Seattle with rain, Portland absolutely shares that reputation. The long-term climate here is characterized by heavy, consistent moisture, especially from fall through spring.
And what's fascinating, according to the sources, is that it's not necessarily the intensity that defines Portland's climate, but the persistence.
Exactly.
It's often characterized as drizzly, gray, and overcast rather than, heavy tropical downpours. That constant damp presence is the atmospheric baseline.
And that consistency defines life there. Think about what that means for architecture, moss, and mold are constant battles. Or infrastructure. They rarely need snowplows, but they need to manage water runoff constantly. That persistent gray is the climate. The sources noted that wonderful local joke about it.
Oh, the one about rust.
Yes. The Portlanders don't tan, they rust.
I appreciate that joke because it just encapsulates how climate fundamentally shapes local culture and even, personal appearance standards.
It does.
Now, let's pivot almost 1,000 miles south, following the coast to the sunny extreme, San Diego, California.
San Diego is the complete antithesis. Its climate is often labeled as Mediterranean, highly consistent, mild, and pleasant year-round. It avoids the intense heat of the interior desert and the persistent cold of the north. Locals truly do experience what feels like eternal spring.
And the statistic that really defines San Diego is just the sheer reliability of the sun. The city sees sunshine almost 300 days a year.
Almost 300 days.
When you have that level of predictability, it has to affect everything from city budgets to social psychology.
It completely changes the risk assessment of daily life. I mean, you can reliably plan a picnic weeks in advance without even checking a forecast.
Right.
However, the sources note an interesting philosophical downside.
What's that?
Residents sometimes report missing the concept of proper seasons.
Ah, that's the crucial insight connection right there. San Diego's fantastic climate is so mild that it flattens the yearly cycle.
It does.
So while the weather is objectively perfect, the lack of dramatic seasonal shifts, the absence of winter's bite or fall spectacle, removes the traditional cultural marker.
Precisely. If you live in a place where the climate is constant, then weather fluctuations are usually just minor inconveniences.
Sure.
But if you live in Portland, where the climate is defined by dampness, a single clear sunny day becomes an immediate celebratory weather event.
So if you're ever trying to explain the difference simply to someone, remember this. The fact that Portland is rainy in November is climate.
That's the expectation.
The fact that it snows unexpectedly in San Diego in January is weather.
That's what you get. Climate is what you expect. Weather is what you get. And this foundational understanding, the expectation versus the reality, is what we use to build the vocabulary of the sky.
Now that we have the long-term pattern set, let's get into the language we use to describe the immediate conditions overhead, starting with cloud coverage and visibility.
Okay.
This is where we encounter the classic conversational trap. Partly cloudy versus partly sunny.
It's a wonderful example of how technical jargon meets human psychology. The sources confirm that for a meteorologist, these two terms are not interchangeable.
Really?
No, even though they sound like mirror images.
So unpack that for us. If I look outside and see a mix of blue sky and clouds, how do I know if the professional is calling it one or the other?
It's all about the ratio. It's about the percentage of the sky covered.
Okay.
When a weather report emphasizes partly cloudy, they are accentuating the positive.
Oh.
The clouds cover perhaps 30 to 40% of the sky, meaning there's significantly more sun than cloud. The mood is generally optimistic.
Got it. So partly cloudy is a good forecast. But if they switch to partly sunny...
Well, then they are tempering expectations. Partly sunny often implies a greater cloud coverage, maybe 60 to 70%. The sun is fighting to break through, but the clouds are dominating the visual field. It's a gloomier forecast than partly cloudy, even though both technically describe a mix.
That's a powerful linguistic distinction. By choosing one phrase over the other, the meteorologist is subtly communicating the emotional impact of the day.
Exactly.
Beyond the parts, we have the extremes of visibility.
Absolutely. At the top end, we have clear skies or sunny skies, unobstructed blue. Then there is overcast.
Right, which is just wall-to-wall gray.
That's it. The entire sky is covered. The clouds are typically uniform, gray, and heavy, often creating a gloomy, diffuse light. It's the visual sign of impending rain or simply a day lagging energy.
And when visibility really drops, we get foggy conditions. This is essentially a cloud that is formed at ground level, drastically reducing the distance we can see. But it's crucial to distinguish this from hazy conditions.
That distinction is key. Fog is condensation. It's water vapor saturating the air near the ground.
Right.
Haze, however, is caused by tiny airborne solid particles, dust, smoke, or pollutants. Haze scatters light, giving the air a milky or reddish tint, and it doesn't necessarily mean the air is saturated with moisture.
So, like the pollution haze over a major city versus the moisture fog that rolls in off the ocean.
Two completely different things with a similar effect on visibility.
Moving beyond visibility, let's tackle the general term precipitation.
Okay.
This is the scientific term for any form of water falling from the sky. The most common form, of course, is rain, but the intensity matters a great deal.
It does. We have the light end, drizzle. These are small, fine droplets, often characterized by that persistent dampness we discussed in Portland.
More irritating than anything else.
Yes, often more irritating than impactful.
And the high end is a downpour or heavy rain. This is when large amounts of water fall quickly, sometimes so intensely that visibility just drops immediately.
Right. The sources note the colorful term cloudburst, which perfectly captures that sudden, intense release of water, often associated with summer thunderstorms.
And that leads us directly to storm dynamics. A thunderstorm requires two main components. You have lightning, which is the electrical discharge.
A sudden, dramatic equalization of charge between clouds or between clouds and the ground.
And thunder is merely the sound that follows.
Right.
It's the sound wave created by the rapid, explosive heating of the air immediately surrounding that lightning channel. Since light travels infinitely faster than sound, we see the flash first, then we hear the boom.
Which brings us back to that marvelous nugget from the sources, the practical application of that physics.
Being able to estimate the distance?
Yes, you can estimate lightning distance. The rule is beautifully simple and incredibly useful for personal safety.
Okay, let's explain the mechanism thoroughly. You see the flash of lightning, you start counting the seconds immediately. Once you hear the thunder, you stop counting. Why 5 seconds?
Because sound travels approximately 1 mile every 5 seconds through the air.
It's that simple.
It is. So if you count 15 seconds between the flash and the sound, you divide 15 by 5, and you know the lightning struck 3 miles away. It's a quick, life-saving calculation that links meteorology directly to practical geometry.
Moving on to frozen forms, because the difference between these is often lost in everyday conversation. We have snow, sleet, and hail.
3 very different things. Snow is the classic. Water vapor in the upper atmosphere sublimates directly into ice crystals.
So it needs to be freezing all the way down.
It requires freezing temperatures through the entire atmospheric column down to the ground.
Sleet is different.
Very different. It starts as liquid rain higher up, but then it falls through a shallow layer of freezing air near the surface, turning the drops into ice pellets before they hit the ground.
Right, they bounce when they land.
They bounce. And hail is entirely separate. Hail forms during powerful thunderstorms, often even in warm weather.
Which is strange to think about.
It is. Water droplets are caught in strong updrafts and carried high above the freezing level where they freeze. They keep collecting more water, get heavier, and are thrown back up again and again till they are too heavy for the updraft and fall as lumps of ice.
That cyclical process is why hail can grow into those large, irregular balls.
Exactly.
Finally, we address wind terminology. Wind speed is critical for safety and comfort. Light winds are soft, gentle breezes, but as intensity increases, we move up the scale.
We eventually reach gales, which are very strong, sustained winds that make walking difficult and can cause minor structural damage.
And then, of course, the most intense rotating systems classified by wind speed, such as hurricanes in our part of the world.
Or typhoons in the Northwest Pacific. Same storm, different name.
The distinction between a breeze and a gale is the difference between enjoying a nice day on the porch and needing to secure all your outdoor furniture. That vocabulary gives immediate context to the level of disruption and effort required. Let's shift from the movement of the air and water to its thermal state. This section addresses the primary confusion point for global communication, the duel between Fahrenheit and Celsius.
It's the metric system divide applied to temperature, isn't it? The United States clings primarily to Fahrenheit, or F, developed by Daniel Gabriel Fahrenheit.
While the vast majority of the rest of the world utilizes Celsius, or C, also known as centigrade, developed by Anders Celsius.
Right. And to properly contextualize any reported temperature, you need to internalize the key benchmarks. You need the anchors.
So what are they?
The scientific anchors are based on the properties of water. Water freezes at 32 degrees Fahrenheit, which is 0 degrees Celsius.
Okay, that's the big one to remember.
That's number one. And water boils at 212 degrees Fahrenheit, or 100 degrees Celsius.
That 100-degree difference between freezing and boiling in Celsius, making it centigrade, is so intuitive. It's part of the reason it's the global standard.
It is. But for those used to Fahrenheit, we often perceive temperature differences more acutely because the scale is more granular.
Meaning?
A 1-degree change in Fahrenheit is a smaller step than a 1-degree change in Celsius. That's why Fahrenheit can sometimes feel more descriptive for daily comfort. A range of 70 to 80 F is perfect.
Right.
The corresponding Celsius range is 21 to about 26.5 C. Both communicate comfort, but the Fahrenheit scale spreads out the human comfort zone a bit more widely.
To move from pure numbers to conversational feeling, we rely on descriptive adjectives. Let's map out the spectrum of cold.
Starting mildly cold, we have chilly or cool. You need a light sweater.
Yeah.
Then cold, requiring a full jacket.
Then it gets more serious.
Right. Moving toward extremes, freezing implies temperatures near that 32 F0C mark where water turns to ice. And finally, frigid, which suggests deep, dangerous cold, demanding heavy insulation.
And the warm spectrum follows a similar intensity curve. Mild is comfortable and pleasant. Warm is nice, but maybe requires fewer layers. Hot means you start sweating.
And then sweltering, uncomfortably hot and often humid. And the extreme, scorching, implying intense, potentially dangerous heat, often associated with the sun's direct intensity.
These adjectives bridge the gap between objective data and subjective experience, which is crucial because our subjective experience is what we talk about most.
It is.
And that brings us to the most vital part of this section, the feels like factor, or apparent temperature.
This is where science gets personal. The apparent temperature is what you actually need to check before leaving the house. It incorporates factors that modify heat transfer between your body and the environment.
And what are the two primary factors?
Humidity and wind chill. These two elements fundamentally change how quickly your body loses or gains heat, often making the thermometer reading almost irrelevant to true comfort or danger.
Let's unpack the humidity impact first. High humidity makes warm temperatures feel significantly hotter. The sources state that 85 degrees Fahrenheit on a humid day might feel like 95 degrees.
It can, easily.
What's the physical mechanism at play?
It relates entirely to evaporative cooling. When we overheat, our bodies release sweat. The evaporation of that sweat from our skin is what cools us down.
How?
It requires energy or heat to turn liquid water into gas. and that energy is drawn from the body's surface.
So if the air is already saturated with moisture, high humidity, there's no space for our sweat to evaporate.
Exactly. Our primary cooling mechanism shuts down. The sweat just stays on our skin. We feel sticky and miserable, and the heat builds up rapidly. It's a physiological danger, making highly humid temperatures much more perilous than the same temperature in a dry desert climate.
Conversely, in the winter, we have the wind chill impact. This is the feeling of increased cold due to the wind. The sources note that 30 degrees Fahrenheit might feel like 15 degrees with a strong wind. How does wind create that dramatic perceived drop?
This is a textbook example of convection. Your body naturally warms a thin insulating layer of air immediately next to your skin. We call this the boundary layer.
Okay.
This layer traps your heat, protecting you from the colder air mass outside of it.
And the wind destroys that protection?
It just strips it away. The wind, or convection, constantly and aggressively strips that warm, insulating boundary layer away.
So your body has to work harder.
Your body is then forced to expend energy constantly, calories, metabolic effort, to create a new warm layer, only for the wind to steal it again instantly. The faster the wind, the faster the heat is removed, and the colder you feel.
Understanding apparent temperature is essential for preparedness. It tells you whether you need an umbrella, a bottle of water, or a specialized winter shell, regardless of the simple number on the thermometer.
It's the most important number on the forecast, really.
Now we elevate the conversation to the macro scale, the 4 seasons. These aren't just weather periods. They are cultural epochs that dictate human activities, holidays, and even emotional states.
Definitely. And we'll focus primarily on the Northern Hemisphere timing.
Let's start with spring, typically running from the equinox in March through May. The overriding theme is renewal, rebirth, and transition.
This is the era of rising expectations. Key characteristics include the gradual, often unpredictable, warming of temperatures, and most importantly, the acceleration of daylight hours. We leave the darkness of winter behind.
And this lengthening daylight triggers the botanical world. Flowers bloom, and deciduous trees shed their winter dormancy, growing new leaves.
And that unpredictable weather is a hallmark. The sources use the classic expression, April showers bring May flowers. This heavy rain is not an inconvenience. It's an absolute necessity for the ensuing growth.
And culturally, the sources point to spring fever. Is that a real thing?
It's a real psychological phenomenon. After months of winter confinement, the increasing light and warmth create restlessness, a desire to be outdoors, and a distinct lift in mood.
But there are downsides, too. We have to acknowledge the physical aftermath of winter.
Oh, absolutely. Mud season. As the frozen ground thaws and the heavy spring rains fall, many regions experience a period of intense mud, affecting travel and outdoor work.
And for some places, spring is actually the most dangerous time of year.
That's right. In many parts of the world, spring marks the beginning of the most severe weather season, particularly for tornadoes and intense convective storms.
Moving into summer, from June to August, culminating in the summer solstice, the longest day of the year. The theme here is warmth, abundance, and maximized outdoor living.
The weather is characterized by high temperatures and abundant sunshine. Humidity often spikes, creating those sweltering conditions we just talked about.
So descriptive language like boiling or scorcher becomes routine.
Exactly. And the cultural expressions are immediate. Beaches, pools, barbecues, festivals, and concerts. Summer is defined by leisure, heavily facilitated by the school calendar, which provides a 3-month break for children driving family vacations and road trips.
But we should note the regional variances.
We should.
While we talk about sunshine in certain tropical climates, this period is defined by the rainy season, or monsoon, with heavy, predictable daily downpours.
And meteorologically, it's interesting to remember the slight delay in heating. The peak temperature of the day usually isn't noon, but 2 to 4 p.m.
Right, because the Earth's atmosphere needs time to fully absorb and then release the midday solar energy.
That's right. And in cities, you get the urban heat island effect in full swing, where concrete and asphalt absorb and retain heat much more effectively than natural landscapes, making cities significantly hotter than surrounding rural areas in the summer.
Transitioning next to fall, or autumn, from September to November, this is the great balancing act. Cooling temperatures, noticeably shortening days, and the shift toward introspection.
And the primary visual event is the fall foliage.
So what's the chemistry behind that?
As the days shorten, deciduous trees stop producing chlorophyll, that's the green pigment. This allows the underlying pigments, the reds, oranges, and yellows, to finally shine through before the leaves drop.
And this event drives significant tourist travel, something known as leaf peeping.
It does. Weather-wise, fall is highly variable. Early September can feel like an extension of summer, yet by late November, most northern regions are bracing for frost and potentially early snowfall. It's a preparation season.
Preparation, which includes the harvest, historically the most crucial time of year for human survival, and preparing homes for winter.
Culturally, it brings Halloween, Thanksgiving, and that complicated shift out of daylight saving time, where the sudden early darkness further signals the end of the year. And of course, fall also marks the peak of hurricane season in the Atlantic basin, often peaking in September.
Finally, we confront winter, typically December to February. The theme is the coldest season, defined by the shortest days and longest nights, centered around the winter solstice near December 21st.
And we really need to nail the hazard vocabulary here, as safety is paramount.
Let's clarify three types of ice. We have frost, which is a thin layer of ice crystals that forms on surfaces when humidity freezes.
Right. Then we have general ice, formed from liquid water freezing,
And then the silent killer, black ice.
which is not actually black.
No, it's a thin, transparent glaze of ice on a surface that is so clear it takes on the color of the asphalt beneath it, making it nearly invisible to drivers and pedestrians.
It creates extreme slipperiness without any visual warning, leading to countless accidents.
And for severe weather, we have blizzards. Crucially, blizzards are defined by a combination of factors, not just heavy snow.
That's the key. They require strong winds, often 35 miles per hour or more, and visibility reduced to a quarter mile or less for a sustained period. This combination makes travel impossible and life-threatening.
Culturally, winter is the season of forced closeness. It's when activities pivot to skiing, snowboarding, or just staying indoors with the concept of hidge.
That cultural focus on coziness and comfort. However, the lack of light also contributes to seasonal affective disorder, or SAD, where the lack of sunlight leads to depressive symptoms, reinforcing that powerful psychological link between atmosphere and mood.
The cyclical nature of these seasons and the profound differences between them truly underline how our expectation of climate defines our yearly lives. We've built the science, now let's explore the poetry. Weather concepts leap off the forecast page and become integral to our figurative language, offering powerful metaphors for human experience.
They really do.
Here's where it gets really interesting.
Well, idioms demonstrate the universal relatability of the weather. Everyone knows what a storm feels like, so using it metaphorically communicates a feeling instantly.
Let's decode the common idioms in your source material, starting with one we use constantly. Under the weather. What's the origin there?
Well, it's difficult to pin down exactly, but the most popular theory links this to sailing. When sailors felt sick, they were sent under the deck to escape the heavy motions of the ship and the exposure to the elements.
So literally sheltered from the weather.
Exactly. It's a polite, slightly vague way of saying you're unwell.
Next, a phrase of resilience and hope. Every cloud has a silver lining.
Clouds bring rain and gloom, symbolizing trouble. But the sun shining through from behind the cloud creates a bright edge, a silver lining.
Right.
It's a mandate for optimism. No matter how bad the situation, there's always some positive aspect or lesson to be found within it.
And the pessimistic but often frustratingly accurate counterpart, it never rains but it pours.
This is a comment on momentum. It suggests that difficult or negative events rarely happen in isolation. When you face one problem, the rain, it often brings a host of others simultaneously. The pouring.
Misfortunes arriving in clusters.
That's the idea.
Let's get into conflict.
To steal someone's thunder.
This idiom actually has a fascinating traceable theatrical origin from the early 18th century.
Oh, really?
Yeah, a playwright named John Dennis invented a sound effect for thunder using sheets of tin. When his play failed, other theaters stole his successful sound effect for their own plays.
So his thunder was stolen.
Literally. Figuratively, it means taking credit or upstaging someone at their moment of triumph.
A fun one regarding overreaction. A storm in a teacup. The visual is perfect. A tiny, contained space, the teacup, experiencing a violent storm. It's the perfect description for a disproportionate fuss or worry over something completely trivial or unimportant.
It just minimizes the drama instantly.
Instantly.
If someone is ecstatic, they are on cloud 9.
This phrase is directly rooted in early 20th century meteorological classifications. Cloud 9 was one of the highest categories of clouds, the cumulonimbus, signifying the highest reachable point.
So to be there is to feel extreme joy and floating euphoria, far removed from earthly problems.
Obviously.
And practical financial planning, to save something for a rainy day.
A rainy day symbolizes a time of need, difficulty, or unexpected expense. This is universal advice, especially historically, encouraging prudence and resource conservation, usually money, to prepare for future hardship.
And finally, the ultimate promise. Come rain or shine.
This is a declaration of unwavering commitment. The person is pledging to complete a task or maintain a promise, regardless of any external circumstances or difficulties, drawing on the unpredictable nature of weather as the ultimate variable.
Beyond the idioms, the sources emphasize the sheer cultural prominence of weather as small talk. Why is this our default social tool, especially in English-speaking cultures?
It really boils down to two factors: immediacy and equality.
Okay.
Weather is an immediate, shared reality. Whether you are rich or poor, or on opposite ends of the political spectrum, you're experiencing the same air pressure, temperature, and cloud cover,
It requires zero sensitive background knowledge.
making it a safe, non-controversial entry point into any conversation.
It's a social bridge, allowing people to transition smoothly from silence to a deeper topic. The common starters are deceptively simple. How's the weather treating you?
And you share the misery or the joy. If it's beautiful, you affirm the shared enjoyment. Beautiful day, isn't it? We certainly earned this sunshine.
Or if it's terrible, the shared complaint creates instant camaraderie. Dreadful out there today. I hope this rain passes soon.
Exactly.
Linguistically, mastering the use of it as the subject, it's raining, it was cold this morning, combined with those precise descriptive adjectives, provides the listener with the structural competence to handle 90% of informal social interactions confidently.
It's the easiest way to connect.
In our final section, we move from observation to anticipation. We're going to solidify the necessary distinction between climate and weather one last time, and then look at the complex mechanics that allow modern meteorologists to predict the future.
And it's necessary to re-emphasize the formal definitions. Weather is the state of the atmosphere right now or in the very near future at a specific location. It's short-term and volatile.
And climate is the long-term statistical average of weather in that region, typically calculated over a 30-year period.
Right.
It dictates the expected norm, which is why we have distinct climate zones.
Exactly. The sources define 5 main zones.
Hmm.
Tropical, which is hot and rainy; dry, arid or semi-arid; temperate, mild to warm summers; cool winters like much of Europe or the U.S. East Coast;
Continental, with hot summers, cold winters, often in inland areas; and polar, which is extreme cold.
Your climate zone tells you what you must expect and prepare for year after year.
Now let's tackle the forecasting gap. How do meteorologists bridge the expected climate with the actual daily weather? How weather forecasts are made? This is where massive technological power comes into play.
Modern forecasting is driven by a concept called numerical weather prediction, or NWP. This involves creating incredibly complex mathematical computer models that simulate the atmosphere based on current conditions.
And these models process data from trillions of input points.
They do, and the inputs come from a dizzying array of sophisticated tools. We rely heavily on weather satellites, some in geostationary orbit that stay over the same point to constantly monitor large areas.
And others in polar orbit that circle the globe, capturing detailed cross-sections of the atmosphere.
We also use ground-based radar systems, which emit radio waves that bounce off precipitation particles.
Like rain, snow, hail.
Exactly. By analyzing the returning signal, meteorologists can determine the location, intensity, and direction of storms. This is critical for short-term severe weather warnings.
And we still use the more traditional physical tools like weather balloons, right?
We do. They carry sensors called radiosondes high into the atmosphere to measure temperature, air pressure, and humidity directly. All this raw data is fed into the NWP models.
And the models analyze key factors like air pressure, which drives wind,
Humidity, which dictates cloud formation and potential precipitation in changes in temperature gradients. The complexity arises because the atmosphere is inherently chaotic, meaning small errors in initial measurements can lead to large errors in long-term predictions.
A modern forecast provides several key elements we need to be able to decode. Beyond the high and low temperatures, the most important element for daily planning is the chance of precipitation, often expressed as a percentage.
And this number is universally misunderstood. But the sources give us the precise technical definition.
So what is it?
If a forecast says 30% chance of rain, most people think either 30% of the forecast area will get rain or it will rain for 30% of the time. Neither is correct.
So what does it actually mean?
It represents a probability of occurrence. Specifically, it means there is a 30% probability that at least zero point zero 0.01 inches of rain will fall at any given point within the forecast area during the specified time period.
So it's a statement about the confidence in the model's ability to predict rain at all.
That's it exactly. That distinction is vital. It means a low percentage isn't necessarily about coverage, but about the forecaster's confidence level.
We also need to pay close attention to wind.
Forecasts specify wind speed and, crucially, direction. And remember, wind direction is always specified by where the wind is coming from,
So a north wind blows from the north to the south.
bringing colder air masses. And the south wind blows from the south to the north, typically bringing warmer, moister air.
And finally, the UV index, a public health metric. This indicates the strength of the sun's ultraviolet radiation, ranging from low to extreme.
And it directly correlates with the need for sun protection, linking the weather to our long-term health.
But as powerful as all this technology is, the sources firmly remind us of the reliability check.
Absolutely. Forecasts become dramatically less reliable the further out they predict. Today's forecast is highly accurate. Next week's is merely a guide. The chaotic nature of the atmosphere ensures that long-term precision remains the biggest challenge in meteorology.
So what does this all mean?
It means you have moved far beyond simple observations. You now have a robust, integrated toolkit. The scientific language to describe a downpour versus a drizzle, the understanding of why 85 degrees can feel like 95, and the context of seasonal cycles that shape our calendar. You can engage confidently in any conversation about the atmosphere.
You can describe the weather not just with passion, but with precision, and you can understand the deep cultural roots of phrases like on cloud nine and save it for a rainy day.
We encourage you to practice. When you check the forecast tonight, look specifically for the apparent temperature, the UV index, and the wind direction. Try to use one of the idioms we discuss tomorrow. Fluency comes from application.
And as we conclude this deep dive, let's leave you with one final provocative thought that ties everything together. We've seen how weather affects our mood, our safety, and our daily plans. We've seen how climate governs infrastructure and culture, particularly through the rhythm of the seasons.
It really does.
So since human life is so intrinsically linked to these predictable cycles, the harvest in fall, the rest in winter, the renewal in spring, what impact does having or not having distinct four-season climates have on the long-term culture and collective mentality of a community?
It's a great question.
If your community lives in eternal spring, does it lose some of the drive for renewal or the cultural markers that define a year?
That cyclical reliance shapes human experience, economy, and psychology more deeply than we often pause to consider. Until next time, keep observing the sky.